Okay, good day everyone. Let's start. For some reasons there is far less people than usually, but okay. So the topic of our today discussion is making steps from regression models that we already, at least in some clue, know how to solve, to the classification problems, or maybe some more general. Okay, let me briefly introduce the plan of the lecture, and then we will follow it. So we know how to solve linear regression problem, but there is actually two restrictions of the whole beauty of our knowledge, that we know how to fit a linear model and only to the continuous response. So all problems that we solved so far as target variable contain the continuous one, which is one-dimensional and take any values that we could expect. Okay, so there is two constraints and we need to deal with them both, but let's do it step by step. Let's start from the second one. Let's break the constraints that we need to fit our model to the continuous response. So why is this important at all? So there's a couple of simple examples that to show that. So first of all, of course, it's a classification problems, binary classification when our output is 0 or could be only 0 or 1. So we have two classes, or if we have many classes, okay, it will be, we can list them as k numbers for k classes. Other example is not maybe so far discussed in introduction in machine learning course, but still it's very practice problem when we have some kind of count problems. So when we would like to count the number of events that occurs in some time. So it could be earthquakes, it could be disorders in the some fabric to manufacture, it could be a number of infected people. So the main restriction in all these cases that we need to get a clue to our model that our output is a positive and only integer positive number. Okay, if we can deal with this kind of limitations, if we could somehow to develop general way how to imply these constraints of the domain of our target variable in our model, then make steps for nonlinear model is much more simpler, because it's more conceptual step how to imply these constraints. Besides that, linear models are already very useful. So basically, with table data, all models are mostly linear. Okay, so we have two roads to solution, how to break the constraint on continuous response. So the first one is a probabilistic point of view, and it gives for us some general framework. We could develop it further, we could solve, we could find a way to how to imply this constraint on any restricted domain of our target variable, not only for classification. Other point of view is machine learning point of view. It's somehow ad hoc adjusting of the optimization problems that we solve. It has its benefits, but for each different domain constraint, we need somehow to develop a new point of view how to modify our optimization problem. And it's not like, not for my point of view, it's not very beautiful, not very useful, because for each problem we need to somehow develop separate way of thinking about it, and it's not satisfying, at least. Okay, we will discuss today both. We will start from the first one, and so it's general, it's a benefit of it, but the cost of this, it's a lot of formality, and so I will draw a lot of equations. It's a bit obscure, hard to follow, but we have a generality. Machine learning approach has some geometrical sense, at least of writing equations. We will just take a look on some pictures and we'll totally understand what we are doing and why that. But this simplicity and some geometrical beauty come in cost of ad hoc solving each problem. Basically, for first approach, we will touch classification and counting problems, and for ML approach, we will only touch classification problems, because at least I don't know software way how to, from like ML point, machine learning point of sight, generalize it to counting problems. Okay, also I would like to mention that basically statistical or probabilistic approach has its own very rich geometry, but it's much more like formal, at much more formality cost and some definitions that I don't want to touch. But I just want you to say that it exists. Okay, so let me start our way in the first part, in the statistical point of view, to generalize problems. Okay, and in order to do this, I will share my doodle screen. Actually, don't hesitate to interrupt me to write in the chat any questions. I see the chat straightforward on my eyes, so I will notice that you're writing something and read it. Okay. Also, let me just a second. I will open a timer to not to spend too much your time. Okay, let's recap in few sentences what is linear regression, because it is our building block that we want to generalize. We would like to make some steps from linear regression to classification problems, but we would like to save this whole framework that we already know, because why to waste our knowledge? We already know something, let's only develop it, not totally forget. So what we are given? We are given some data set of points where each xn is assumed to be some d-dimensional vector, and for y we assume that okay, it's a real value but one-dimensional. So what we train? We say okay, we would like to sum our loss over the whole bunch of points, and we would like to minimize the difference between the actual target value and our model, which is linear. And we would like to minimize this over parameters b. Okay, in some sense, we could develop it further and say, okay, we have some ways, let's say, for each observation, we could modify our loss for this. So could we find some statistical interpretation of this procedure that we make some statistical model of this, but with the same optimization problems? And okay, we could try to say the following. Let we observe the conditional distribution of yn, and let it be normal distribution with some mean function and some noise, and let it also be for each observation different. So I put here the index n. Okay, so then we could say, okay, we would like to fit this model. So what is this mu of x sign? This is conditional expectation of yn, and we, like, as we would like to match this optimization problem, we say, okay, it's linear model, inner product of our features xn and parameters beta. Okay, then for statistical model, we know that the general approach to fit is it's maximum likelihood estimation. So let's do this. So in order to do this, we say, okay, we would like to maximize the sum of the log densities estimated at each point with mean of our model and some noise. We assume that noise is given for us. Okay, we can open brackets and leave only term which is depend. Oh, sorry. Only depend over beta, and this will be this one guy. Okay, and then I could a bit modify it, multiply by -2, just to keep it more clear. And then it's minimization problem. Okay, so what you can see is that we developed a statistical model, very simple one, but this is exactly matching what we done before. So this is our optimization problem for linear regression, which we had developed from pure like machine learning approach. We would like to minimize the loss. We could we have the model. We could add some weights to our data set points, and this corresponds to this model that we have a normal distribution with conditional mean, and actually then we see that our model is model not each response individually, but it develop the model for the conditional expectation of our target variable given some features, and that makes sense. Okay, then the reasonable question is, what is we select the normal distribution? And one of the possible answers is because we just starting from the matching the domain. So in the linear regression model, we say, okay, our target variable is real one, so it's on the whole line. So we need to develop some distribution that has a support the whole domain, and this is like the normal one. Okay, then if we have some problem when, let's say, this guy is just positive integers, or this guy is could take two classes 0 and 1, and we need to do something that's similar. Let's model some conditional mean of some distribution, but with that it's matching the domain of our this target distribution. And let me then, so this is expectation is taken with some distribution which is matches the domain which we solve the problem. Okay, and of course we would like to say okay, and we will still have a linear model. So let this guy, let me put n here, let this guy be linear regression. And you see the problem. The problem is that this guy is lie in some domain. It may be different because it's expectation. So the expectation could lie not in range of integer numbers, but still it would be at least inside it. So for example, for this case, the expectation could not be greater than, could not be less than 0, cannot be greater than 1. And this guy is taking values again in the real domain. So then we need to make this step. We need to find some, it's called link function. And then that linear regression match this value. The only problem that we need to solve is we need to find the way. So what is this link function? How it depends on the distribution which we take expectation with respect to. And how we find this guy in this approach of maximum likelihood. So these two problems, and okay, we are going to address them. Before, let me introduce some very small example, but to just keep in mind something real. So let be nu n is expected number of disease on the day 10. And I emphasize your intention to the word expected number. So like average number of disease cases by day. So, and we could say, okay, we all will die and the model is terrible. We have some exponential growth. So as much days starting, then new cases grow exponentially. Then we, for example, could take logarithms, and this guy is lie on the real line, and this will be like this. And from this, you could recognize a linear model. So in some way, so in this simple case, it's easily seen what is ring function. When you see that something is equal to exponential of something linear, then just you can easily take the logarithm and say, okay, this is my model. A bit trick here that this is not observation, it's expected number. And so we will work around it in like some mathematical terms. Okay, and to do this, we need to develop our knowledge around exponential family of distributions. So what it is, let's consider some density function with parameters theta over the y. Let's say that it's not not quite freedom to have it, but in some particular form. So let it be exponential of the inner product of the parameters theta and some sufficient statistic of y. And then let's make minus b, because we need to normalize, so any density function should be integrated to 1. And for some technical reasons, let's also put here this term. Okay, where this guy is equal to what? To the logarithm of the integral of all other functions, because we need density to be integrated to 1. Okay, so then what can we do? Let's take a look on the logarithm of this guy. It will be quite simple. So we have some linear term minus log of normalization constant plus log of this guy. So as we machine learners, we would like to take logarithms, of course, or take gradient of the logarithm. So and it will be equal to some statistics of our data of y minus the gradient with respect to parameters of the normalizing constant. Okay, but who is this guy? Let's see for what it's equal. Let's start just by doing what we can do. Just take the gradient. Okay, sorry, there is no logger because it was inside the exponent. Okay. So it's just the gradient of already log normalizer. So it's the logarithm of its definition. We put, okay, just take the gradient. The gradient of the logarithm is the ratio of what inside the logarithm. So, okay, we wrote it here. Then we need to take the gradient of what is inside the logarithm, the exponential. So it's remaining the same. Then we need to take the expectation what is, or the gradient of what inside the exponential. So this inner product of theta and t. So it just will be as gradient of linear function, just t. And let me write here these terms. So we could recognize in this because so this guy divided by this is exactly our distribution. Let me mark this. So this guy and this guy together give us again our density, and this guy, of course. So this is just the expectation of this guy. Okay. So what we get? We get that the gradient of this our guy is equal to this statistics minus expectation of them. So then it's easy to see that expectation of the gradient is equal to 0. And we will need this. And also, as I have some free space here, we could see what is MLE solution and MLE's maximum likelihood estimation for this exponential family densities. It's quite simple. So what we do, we just write the sum of the densities of the logarithms. So what we get, we have here parameters. Yeah. Oh, so it's I already take the gradient. So it should be equal to 0 as first order condition. And as we would like to solve them, we see that this guy should be equal to this. Oh no, sorry. Okay, let me write it more correct because I make in inequities. So what we would like to do? We would like to maximize the sum of log densities with respect to parameters. Okay, it's equal to the sum. Here we've written the logarithm, and we're only interested in these two terms because they depend over theta. This term and this identical terms. Okay. So then we take the gradient. Let me write it. Take the gradient. And obtain the sum. There is no index in here. And solving it, we have okay. So this is a solution, and we know that this guy is equal to expectation. So from one side we have empirical average, and this guy is true average. So what is this? Is that here we just sum up all statistics over our data set, what we actually observe. And here we say that, okay, then the gradient of our model, well, so then the parameters of our model should be equal to such value that if we take the real expectation of our model, of our target variable, it should match that what we observe. And this is very natural. So we would like to just make such parameters that the expectation of our target variable is the same as what we observe. Also, let me know that why this is enough condition, because problem is convex. I would now show it, but if you would like, you can just take the, so this term is linear, and you just need to take the find Hessian of this and check it. It's a bit routine, but you can check it. Okay, but why it was what's the clue? What is the relation to our problem? You see here that what we would like to do about is we say, okay, we need to find, let me copy this. We need to find something this. It was our dream. And here we see that the gradient of this function from the density b of theta is equal to expectation of some other functions of our variable b. So then if we could inverse this function, we could say that, okay, theta is equal to this guy. Inverse of this function applied to the right side. Okay. And then we could say that, okay, we model our parameter theta is a linear regression. And basically it's what we would like to do. Okay, there is a couple of technical questions here. So this is not exactly our observed y, it's some function of it. It's also like a vector, what is inverse of the vector function, and so on. But we will deal with them because what? Because actually we have very simple situation. We solve for one-dimensional y, at least for now. But actually, with this approach, we could generalize it. We could have multi-class, or we have multi-output regression. But let's solve for one-dimensional y. So y is something that one-dimensional. And we could restrict our densities just to be this guy equal. So what statistics we would like to model our density, it should be our observations. And then it will be much easier. So then we could convert this straightforward to this. Let me formally write it. So let's call it mean statistics only. Okay, let me say that these two assumptions lead to this density. So this both just this guy and this guy just all both numbers, not vectors. Plus some function. So basically we could say that this is about variance and this is about mean. Okay, then let's do this whole stuff again. It would take a logarithm and this will be this guy. Then we know that, okay, let's take the gradient and this will be okay, sorry, this is p. And we know that the expectation of this guy is equal to 0. So then and then we could model the parameters theta be equals this function. Apply to expectation of t equal to theta. And then we could model these parameters of distribution as linear model. And so this is our solution. Okay, it was a bit maybe obscure. So let's get to practical examples. Let's start with Poisson regression. So maybe somebody of you would remind me what is the density function of the Poisson density? Come on, you are like learning on third year. You already have statistics, so you should know what is Poisson density function. Okay, Mikhail, let me ask you. What you guess? What is Mikhail muted himself? What you guess? How do you remember something about Poisson densities, Poisson random variables? Okay, maybe somebody, Vladimir, Vladislav, Alexander, or some could write. Let's make some interaction. Okay. So let me write them. So the density is very simple. What we would like to do. We would like to say that, okay, as much more what we observe, then in some sense less probability. And then to normalize it, we could notice that this guy is just terms from the exponential sequence, and then it will be this one. Okay, then we need to find who is who here. We need to match this for. Then just let's take the log. What we will have here? We will have like minus mu and minus log of this guy. Okay, then we just could see that. Okay, this is y, this is y, this is theta. Okay, then this is theta. But then we need to match this guy to be some function of theta. And here we have a function of mu, or mean parameterization. So let's modify it. So let's say that, okay, theta is equal to log of mu. Then, of course, mu is equal to exponential of theta. And basically, that's it. So what we need to do, we then could solve, like, assume that we observe some data of some xn, yn at x count of diseases, for example. So yn is positive natural numbers. So we solve the MLE problem. Over parameters. Okay, let's write it in more details. So we could write this guy minus this guy, and we would like to maximize it. Okay, then we can say that this guy be theta. Then this guy is the exponential of theta. We would like to maximize this over theta. Now we need somehow introduce that we observe not only y, but also x. So let's model theta as linear model, what we already know this way. So it will be okay, and this is optimization problem that we already know how to solve. We could take the gradients with respect to beta. What it will be? It will be some. Yep. And then we could make one more step. We could write such form. And this equals the gradient of beta. So you can see that what this term is. This is our features. And this is the difference between observation and the conditional expectation of this observation given extent, because it's equal to theta, to what we model here, the mean parameter. And this gives for us some intuition that, well, again, the update of the parameters is reasonable. So the every new bk plus 1 is equal bk plus the sum step the gradient with respect to beta, which is equal modify bk in such direction what is like lie on our error multiplied by value of features. So if we have this error big, it's all affects that the coefficients should be pushed to the direction of these features to modify this error, to reduce it. If on some object this is already matched, so this object doesn't make any influence to our good coefficients. Of course, here is like the sum over the 4 points. Okay, and so the beauty is that then we could all the same to make the classification. Okay, let me ask you a very simple problem. Please say that what is Bernoulli distribution? So we have yn could take two values, 0 and 1. Then how I could write exactly what's the parameters. Okay, let me ask Artyom Chernyshov. Could you please say something about Bernoulli distribution? Guys, actually, I'm not understand why I'm so resistant to make some discussion. Oh, so it's not that much, just so even your wrong guess is okay. Just to not only me to speak, but okay. So I could write it, of course. So what we have here, we have the probability of success. And this is equal, that this guy is equal to 1 in this term and otherwise. And of course, we need that probability B lie between a 0 and 1. Okay, then of course we could take logs. And say, okay, this is equal to this. And this is equal to this. And then we need again to match this term when we have y multiplied by some value. So let it be, just with open bracket, this one, minus plus this term. So okay, clearly this is our data, but how to modify this data? So in this order, we need to find the solution here to inverse this function. So it could be easily done. We could note that okay. Okay, so let's start from that. So we can take the exponential from both sides. Then this will be this. And this again equal to just by dividing over b. Okay, then we could flip it and add 1. And this is b is equal to this. And then we could flip it again and obtain finally that here is this one guy. And this term is something familiar that for you one who was in the data culture courses or some other. This is a sigmoid function. But it's like come not from nowhere, but come from Bernoulli distribution and the link of the probability and mean parameter. Okay. So then I can just plug in this guy to this term and let me do a bit shut up time. Write that it will be equal to this. Okay. Then again, we could model mean value of y as this guy. The derivative of this term. So it will be exponential of this guy and above. So and again it's equal sigmoid function. Yeah. Then we could inverse it and obtain that okay. So the logarithm of this should be equal to theta. And this is called Lagrange function. And this is inverse of sigmoid. As far as we write this, we are done. We say okay. So we would model this Lagrange as again linear function. So then we could again write the NLVR problem. Then okay, we would like to maximize the sum of these guys. What is this? This is likelihood of Bernoulli distribution. And it's natural because we would like to classification problem model the probability of success of y equal to 1. So then we take the gradient. What we obtain. Okay, then we could step a bit and say, okay, we model this again as linear model. We could rewrite this. In this form, just plug in the terms and then take the gradient with respect to beta. What we obtain? We obtain this and this minus here will be this guy, here will be this guy, and taking derivative inside exponential will be this guy, and this should be equal to 0. Again, we can note that we obtain the same result actually. Here's our gradient. And again, inside we have what? We have difference between our observation and conditional expectation multiplied by the features. And let me like stress on this, that this is the same for logistic regression, which is classification problem for binary outputs, but for Poisson regression, which is regression with regression problem, not classification, but for outputs which is integer, we have the same gradient. So the conditional expectation is different, but the gradient was features multiplied by the difference of the observable, what we observe point, minus its conditional expectation. And like this is the beauty of the whole framework, that we just need to take the such distribution that we match domain, the range of our target variable, and then even the gradient updates are equal. They are just features multiplied by difference of observable minus conditional expectation, which is defined by our distribution that we select. So as programmers, you can see that like this, how to easily implement it. So you just write the basic class of generalized linear models, and fit method contains that, okay, the gradient will be steps of the gradient, and the gradient is equal observable point from data set minus conditional expectation of it. And then for different distributions, you just rewrite a bit define what is conditional expectation for this distribution. And the whole other training stuff is keeping the same. And let me also show you the Hessian. What is conditional expectation? So let's consider some particular example, and then if so assume that we model some distribution, let's say normal, of y's, and we say, okay, it has mean mu, so okay, some variance sigma, and then expectation of mu equal to of y equal to mu. Then you can say, okay, I can do better. Let for some y n particular, okay, for some y, its expectation is equal to x transpose. Okay, let's write it this way. Plus sigma squared. Yeah, then, okay, expectation of this, let's call it y with wave is equal x transpose beta. Just by definition, we say that. You see here that we find this expectation when we was given information about features. Then we could say that it was this was the distribution of y, and this was distribution of y given x, and then the difference. So when we take in so what we can do, we could take expectation of y conditional on x. It's a conditional expectation, and it will be this guy, x transpose beta. Then we could state a question: what is like the distribution, the expectation of y the whole? So then we could decompose it. We could say that this expectation of over the x over this guy, and then it will be this one, and then it will be this one. So I hope you see the difference, that the conditional expectation is taking expectation with presence of some additional information. When you given not the like unconditional distribution of random variable, when this guy, its mean value is fixed. But instead you can say, okay, my distribution, its mean parameter depend of some additional piece of information. In machine learning, it usually features that would observe x. And then its conditional distributions mean is this guy, but of course it also implies that they have an unconditional distribution. It's called full, not distribution expectation. It's called full expectation. Okay, and then when I'm talking about this conditional expectation, this is like this term. Why is this conditional expectation? What is it? Let's thought a bit more about this. Okay, let's also divide over this guy to get more familiar. Okay, we get this. What is it? So here you could recognize that our linear model, xn transpose bit, it's our linear model. But above it we have a sigmoid applied, sigmoid function. And then where our sigmoid function was hiding, it was here. When the expectation of y is equal, like sigmoid function applied to some theta. And here, if we like not observe some additional information, we could stop. We can say, okay, we observe, let's say, 5y equal to 1, 10y equal to 0. Then so the mean value is 1/2. Then probability of y be equal, okay, not 1/2, but it's better, to 1 is equal 10/15. So it's this guy. And then we say, okay, this should be equal to this. And here we could like inverse it. So the theta parameter will be equal to this guy somehow. This parameter is the mean parameter, the parameter of mean value of x, what we need to put to here, to this density. So this is probability density function of Bernoulli distribution. P is the probability of success, but we could rewrite it in terms of theta, because it's the logarithm of ratio of odds. Okay, but we say, okay, it's not enough for us. We observe also some other information. We say, okay, when this guy is equal to 0, this 5 times, let's say x will equal to 1. And when it was 1, x was equal to 2. Okay, and then we need to say, okay, we cannot just say that, okay, this guy. We need to say, so it was equal. So we need to obtain the conditional expectation. And okay, y given that x equal to 1, and other when x equal to 2, and then it will be like 0, and this will be 1, and like make this whole derivations, and then saying, okay, we need this guy to fit each observation when we are given some x. Okay, I hope SEM 9 166 I answer to the questions. So let me. Okay, we could stop on this topic here. I would like to show you the Hessian, but okay, let's skip it. Let's stop here and watch what time we have still. We have 20 minutes. Okay, let's say I have 5 minutes to answer on your questions on this kind of topic. Okay, I guess there is no questions, but when I finish, you could still be here, and I could answer your question. You can ask questions on Russian language, it's okay. But for now, let me then switch to our approach, which we need to discuss, like not statistical approach, but machine learning approach. And that was a code, but much simpler. So what we would like to solve. Okay, for this we will consider only the problems classification, we have two labels, and for now it's more convenient to define classes not as 0 and 1, but as -1 and 1. Okay, we saying, okay, this is our linear model, inner product of features plus bias terms, and it's returned some real number, of course, because you see that we multiply numbers. So what we can do with this, we could apply a function of sign, which is saying, okay, this guy is greater than 0, then I output 1. This guy is less than 0, then I output -1. And this is reasonable because our answers should be -1 and 1. Okay, we're fine with this. So assume that we have just like this one guy, which is always 1, to not to write this guy separately. It's a bit ugly. So we can summarize all our features here. So then we just find inner product, like estimate our usual linear model, and then just take the sign function of it. If our linear model responds something greater than 0, equal to 1, less than 0, equal to -1, so it's kind of classification. How it looks like. So we have a hyperplane, which is defined when all values of x for given weights, which is this summation is equal to 0. And the role of weights here is it's a normal to our plane. Okay, and actually when we in two-dimensional space, and we could easily imagine the normal, you can use words upper and below, and so the all +1 values will be upper the hyperplane, and all other below will be equal to -1. So with this kind, if you could separate your points with this hyperplane, you get your class labels. And here it's like written in words, but the same. So here's example, like hyperplane two-dimensional is a line, normal is pointing in such way. So we have some above, and we put for its sign equal to 1. We have some guys below, we put them signs equal to -1, and this is our classification solution. So if you know how to make this line, which is like put here like in the picture, we could use it as classifier. We can say, okay, if positive, that positive class, if negative, negative class. Okay, but let use some geometrical intuition of here, and like what we expect of these guys. So if some points are close to this line, we're already not very sure what class is it. So this guy is lying on the border, and this guy is like on the border. So strictly speaking, this is still positive and this is still negative, but like we're not very sure. But for these guys, it's deeply positive, and this is deeply negative. So we're sure these two classes. And let's formalize this notion. So we're saying that, okay, let's define the distance between our point to the hyperplane, to the lines that separate our two classes. The larger this guy, then it's like further from the separation line. Okay. So we could say a bit more. So if this guy is positive, and this guy, our label is also positive. This guy is also positive because it's a product of two positive numbers. Also, when this guy's value give us negative value, we no clue how, -100, -1 million, some negative value. And these guys also have, our label is -1. Product of two negative numbers, again, is a positive number. So then we could define that the product of our linear model and the label, and that if it's greater than 0, then we guess right. It was negative and we get negative number. It was positive and we get positive number. If it was not the case, if there are different signs, so it will be less than 0. So here, let me remind you that our classifier gets model composed with a sign function. Okay, but it's like, of course, some functions that take values +1 and -1 is discontinuous function. So, and we know only how to optimize with gradient descent, with something that we can take the gradient. So we make step to something more smooth. We say, okay, we could identify are we correct or we wrong if we take the just product of these guys. It's greater than 0, less than 0. Okay, one more thing that we can do is just saying we not always would like to say that it's positive. If we just positive, if we just less a bit greater than 0, we would like to, for example, mark it as a positive class if it's greater than 100. So it's again a trainable parameter that we can tune to show our confidence. So for example, let's get to this picture again. We're saying, okay, but for these black dots that lie here, very near to the red dots, we don't like to classify them as positive class. We would like increase our threshold, and then line will be go here. For example, it will be of course parallel because we didn't change the slope. We just make an additive push, and so this line dots will be red, and the positive class will be far away. Okay, so we know how to, we get our classifier. It's a sign of this equation. So it's a linear model minus some threshold. We know how to get smoothly, at least in some sense, if we correct prediction or not. We just multiply label with response of our linear model. And if we use threshold, could put it here and saying, okay, if it's positive, we correct, it's negative, we wrong. And so we define the solve, and we would go to the problem of how to train this model. Sorry. So the naive approach is just saying, okay, if labels are the same, we are correct. If labels not the same, we are wrong. It's fine. It's called accuracy. It's reasonable to see how your algorithm, what accuracy it is, but it's not trainable. Why? Again, because we would like to train all on the world with the gradient descent, and the gradient descent is only meaningful when we have smooth functions. This guy, of course, is not smooth, so we need somehow to modify it. Okay, let's make a first step. We could plug in it here and say, okay, let's count how many times we are wrong. So this guy, it should be not equal to our label. But we know how to reformulate it, how to get rid of this sign function. We know that we are wrong when we take the product of our label and our model and compare its sign with 0. And let's call it mi because it's margin. Okay, we rewrite it in this way. Let's make one more step and to make it smooth. In order to do this, let's just plot and see what's this guy. So is this our error rate? If we have it's function of the one number here, m. If it's less than 0, we have, okay, it's a row, it's equal to 1. It's greater than 0, okay, it's a row, not a row, it's equal to 0. And we would like, of course, minimize. The usual way to deal with such kind of problems, when you would like to optimize something, to minimize, but it's not very good function, you can minimize an upper bound on it. So here we could suggest some upper bound, which would be dependent on m, and it will be a smooth function. Let's see. Okay, for example, this one. So what properties here? See, if m is great and positive, what does it mean? It means that we give correct answer, and as it great, take great value, it's far from the separate line. In these terms, for example, it will be this point. This point has a big positive margin. It's lie far away from the separation line. So then we say, okay, if it's very far, we don't need to modify something, and our upper bound then should get close and close to 0. On the other way, if our margin is negative, then we make an error. So if we make an error here, for example, this guy, let it be not red but black, but it's very close to the separate line. So it's error, but not very influence one. It's saying, okay, it's a mistake, but not very much. We are more okay with that. But if we have like black dot here, for example, it will be error and the margin will be very big. And that's saying for us, okay, it's something goes wrong. We make very much error because something that is like lies separate, like alone from the separate line has a error. And then we see that, okay, our upper bound, when the negative margin goes to infinity, should grow up. And it will be okay. So we can rewrite it. We say, okay, we could minimize this, but we cannot. So we will minimize upper bounds. And of course, there are plenty of upper bounds of words that we can define, and then just use gradient descent. And you see here is what is the reason? What is the difference of two approaches? When we discuss the probabilistic or statistical approach, we say, okay, we define the distribution of our outputs and use then maximum likelihood estimation. And this gives us our loss function. But here we have quite a freedom on it. We find with any upper bound. And this is good in some sense because we could somehow ad hoc help ourselves to get rid of some problems. But in other sense, we have some problems because we don't know what we need to make some separate investigation. What is upper bound leads to what? Okay, so we discussed about this one, about logistic, and it will, of course, lead to logistic regression, which we derived. But what I would like to emphasize for you now is that the assumptions that's used for such kind of classification, which is all depends on the margin. This assumption is like crucial because it's saying for us that two classes in some sense compact. What does it mean compact is then when your neighbor is the same as you. And when your neighbor is not classified as not the same as you, then it's huge margin and this row and influence a lot. So for example, if this point will be black, then upper bound of unbounded upper bound of our loss would be modify this line a lot because it's huge margin and error will be white with very high rate. And it will be influenced a lot to this guy. And this is because this algorithm assumes that, okay, all points here is red. It's far away from the separate line. So it should be also red line, a red point, but it's black. So let's modify this line a lot. How to see this mathematically? It's like here. So here we have a huge margin, which is negative. And for these whole lines, green, orange, red, it's unbounded growth. Moreover, it's like, for example, so this color, okay. So the red color is this. So of course it's exponential. Logistic is orange, and so it's a logarithm of exponential. So it's like growth linear. Green one is also like linear growth. And purple one is decay, starting to decay here. And this is very useful. Why? Because if we say, okay, we know from like our machine learning experience that sometimes there is outliers in our data set, and it's okay if there is a point in this a lot inside of our classes. And this is in other case. We don't would like to grow to influence it to whole our procedure. But with these 3 lines, it will like influence exponentially or linearly much. But with purple line, it will say, okay, the weight of this point is bounded with like 2. And so this is the beauty of how we could a bit modify our laws. Okay, this whole we done. We could add regularization, of course. So the whole point is that L1, L2 regularization and all proximal methods that we discuss is all updates will be the same. It will be only a bit modified towards the gradient, but the still updates will the same. Okay, so let me stop here. You will touch quality metrics in classification, so I will publish the slides and you can go it from yourself. And you will discuss it in details in the seminars. Meanwhile, I more would like you to ask me questions, because there was a lot of material and you are very, very, very quiet today, which is unfortunate. So you could ask, you could write, you could ask in Russian, you can write in Russian, whatever. Just give me please some response, some questions, some impressions, something. No questions, thanks for language. So again, did you already like know all this? No. So my speech was so clear that you understand all, have no questions. I guess like it was not so clear. Okay, so clear for understanding. Okay, thank you, but I'm in doubts with that. Okay, so lecture is then ended. I deliver what I wanted. If you have other like duties, feel free to quiet the lecture. If you would like to stay and maybe ask questions not in the presence of the audience, you can do this. I will wait while the whole of you guys will leave the room.